All right, so in this lesson, which is our last lesson, we are talking about two dependent samples, which means we have what are called matched pairs. So in everything in this section, the two samples that we have are dependent, which means that the values from the first sample, I don't know why I have an of there, we don't need that, are in some way related to the values in the second sample. So we can see here down in the example I have that we've got measurements from a right arm and a left arm of the same person. So they're related because the data comes from one person. Sometimes the match might be between a parent and a child, or it could be before and after data. But in some way, those data pieces are related to each other, and there's a correlation for one specific value to another very specific value. So we always have requirements. I've typed those up here at the top. Sample data have to be matched pairs. It will be important on the final exam. It's not going to specifically say these are matched pairs. So you actually need to be able to distinguish, based on doing all of these practice problems will certainly help, data that are related, meaning that are dependent, or data that are not, like we did in section 9.2. So the matched pairs need to be from a simple random sample. So in this case, we have a simple random sample of women. The number of pairs either needs to be greater than 30, or the pairs need to be from a normally distributed population. So we have new symbols because this is the first time we've done matched pairs. So this lowercase d stands for an individual difference in a matched pair. So we might have d sub 1, d sub 2, d sub 3, but we're talking about a single matched pair. Mu d is the mean of the differences in the population. And so our d bar is going to be the mean of the differences in the sample. So when we are trying to do a hypothesis test or a confidence interval, remember that we're trying to apply this to the population. So this is the guy that we are going to be using in our claim, because we're talking about the population when we're making a claim. Then we have S sub d, which is the standard deviation of the differences in the sample, and then n, of course, is our number of pairs. So certainly when we have a small list of data, it wouldn't be too terrible to individually calculate the differences between each matched pair. So I can do 102 minus 175, 101 minus 169, so on and so forth. But when we have a larger list, certainly that becomes very cumbersome. Also, if we have the calculator do this for us, that's going to cut down on our possibility of making careless errors. So we are going to use the lists in our calculator. So we're going to enter the matched pairs into our list 1 and list 2. And we're going to make our list 3 into L1 minus L2. The way that we do that is on the home screen, we type L1 minus L2, and then we do the button that is kind of near the bottom left. It says STO, and then it has like a little arrow on it. So that means store as list 3. So because list 3 contains the differences, and that's what we're looking for, that's the list we're going to use when we run our hypothesis test or confidence interval. In this case, because we're talking about a single mean, because once we found the differences from the two separate samples, it's just one list of data that we're then using. So we're actually going to use for our tests ones that we've already used before, and that's going to be for the hypothesis test, it's choice 2, the t-test. And then for the confidence interval, we're going to use choice 8, which is the t-interval. Okay, so let's go ahead and go through this example here. So first thing we need to do is we need to enter this data into our calculator. So we go to Stat and Edit, and make sure you've cleared out your lists. Remember that you can do that by Stat choice 4 and typing the names if you need to do multiple lists, or in the lists themselves, if you're up in the list, you can press clear. Just don't press delete, because if you press delete, it deletes the entire list itself, which is not a good thing. So in our list 1 is going to be our right arm data. So we've got 102, 101, 94, 79, 79. Then in our list 2, 175, 169, 182, 146, and 144. So we're going to enter that data in our list 2. So 175, 169, 182, 146, 144. Okay. Always, 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 as I've said many times, double check your data entry to make sure you haven't made any mistakes. So I just go through really quick and double check all the values to make sure that they're right, which in this case they are. So now comes the part where we make list 3 into list 1 minus list 2. So go back to your home screen, and then we do second 1 to type L1 minus second 2 to type L2. We use the store as key, and then we're going to store that as list 3, and we're going to press enter. So this, it displays all the differences for you here, but notice that when I go to stat and edit, it's automatically put in there for me. All right, so that can help you save a lot of time. Okay, so part A of our example, now that we actually have our data, is we're going to use a 0.01 significance level to test the claim that there's a difference between the measurements from the right and the left arms. So these are systolic blood pressure measurements from the right and left arms of the same randomly selected women. We are assuming that the sample is from a normally distributed population, which is good because I only have 5 data pieces, so definitely do not have n greater than 30. So just like with every other hypothesis test, we're going to start out with our claim. So as I said at the top, we are going to be using our mu sub d in our claim. So in this case, our claim is that there's a difference, which means that mu sub d is not equal to 0. So in this case, we would say mu sub d less than 0 if we were saying that, right arm is less than left arm. We would say mu sub d greater than 0 if we were saying right arm bigger than left arm. So in this case, because it's just saying there's a difference, if there's a difference, that means that the mean should not be 0. So that is our claim. Our null hypothesis then is that mu sub d equals 0, and our alternative is the same as the claim. So now we are going to look at our various values. Sometimes we are going to be asked to find the individual differences or means and all kinds of different things. So we're going to list those out. So we're going to find D bar, and we are also going to find S sub D for our references here. So the way that we can do that is because I have all my differences in list 3. So way back when, we learned how to find different statistics for a list. So we go to stat calc. We're going to run the one variable statistics, so choose choice 1. And now we're going to be using list 3. And hit calculate. And that's going to give us our values. Now the X bar here, because this is the mean for list 3, this is our D bar, because D bar is the mean of the differences in the samples. So that's negative 72.2, and then it's our SX that we would be using for our S sub D. So we have negative 72.2 for D bar, and we had 9.3, because remember, we should always round our statistics 1 decimal place past the original data, which are whole numbers. So now we're going to look at our actual claim. In this case, this is a two-tailed test. So if alpha is 0.01, that means I have 0.005 on both sides and 0.99 in the middle. So it does not matter which side you find, because remember, on two-tailed tests, we're going to have the plus or minus. So our critical values, there should be 2 of them. We'll have a plus or a minus. So I can either do inverse T of 0.005 with degrees of freedom 4, because there are 5 values here, or I can do inverse T of 0.995 with the same degrees of freedom. And those are going to give us our values. So second distribution, inverse T, 0.005 with degrees of freedom 4. And we get our critical values. Again, this one's the negative. If I did the 0.995, it would give me the positive. So I have plus or minus negative, or plus or minus 4.60 is how it rounds to 2 decimal places. So those are our critical values. Then we're going to run the test so that we can find our test statistic. So go to stat tests, and we're running a t-test. We do not have stats, we have data this time. And our value, our mu sub d, we're comparing it to 0, because that's the value that's in the alternative and null hypotheses. Our list is going to be list 3. Frequency always stays 1, and my alternative hypothesis was a not equal. So choose that one. And when we run the test, here we see both our test statistic and our p-value. So our test statistic was negative 17.34. Our p-value, when we go to use that method, again, we've talked about this before, but make sure you look at the whole thing. This is in scientific notation, so that means take this and move the decimal place 5 places to the left. So that's very, very close to 0, so we're going to just say 0 plus. All right, so critical values. Since my test statistic is negative, I'm only going to compare with the negative. So my rejection region on the negative side, I technically have 2, but I only care about the negative this time. This value right here is negative 4.6. My test statistic is negative 17. It's way over here. So yes, that is in the rejection region. So I'm going to reject the null hypothesis. P-value method, my significance level, my alpha was 0.01. 0 plus is definitely less than that, so we get the same result. Now be careful, I always get people who try to use on the not equal, try to use the warrant rejection. We're only using warrant rejection if the claim includes an equal sign. This is a not equal sign, so we're still using support in this case. So our final conclusion is, because we rejected, that means there is sufficient evidence to support the claim that there is a difference in systolic blood pressure measurements in the right and left arms. All right, last part, construct and interpret the appropriate confidence interval. So go back to our calculator here and go back to stat tests, and this time we're going to run a T interval. So choice 8, again we have data, list 3. Now our C level this time, be careful, this is two-tailed, which means instead of 1 minus 2 alpha, it's just 1 minus alpha. So this is a 0.99 confidence interval that we're constructing. So list 3, frequency 1, our C level in this case should be 0.99. Then go to calculate, and we've got our values. Now, our values, remember, are for mu sub d. So what we are saying from this, I'll let you look at it again, hopefully you've got it on your calculator as well, is that between negative 91.37 and negative 53.03 is where our mu sub d would fall. So this is our confidence interval. Our interpretation would be, since the confidence interval doesn't include 0, there is a difference in right and left arm blood pressure, which there is a difference. So same as this, there is sufficient evidence to support that there's a difference. So we got the same final conclusion as the hypothesis test. If they were to ask, because these are all negatives, that means that really what we're saying is that the mean for right arm is less than the mean for left arm. So sometimes they'll ask it in that way as well. So since both sides are negative, that means that sample 1 had to be less than sample 2. All right, that wraps up all of our lessons. So just heading now to our final quiz and to the final exam.